All right, it is after 11:30. The microphone is working. The recording is on. Welcome everyone to another week of Chemistry 300. Last week, we started our first real topic of chemistry, something I do expect you to understand, which is the concept of atoms, molecules, ions, as well as the periodic table. Just a quick review of what we went over, at least the most pertinent parts to today is from the groups, we do know the number of valence electrons in each group, such that group 1 has 1 valence electron, group 2 has 2, 13 has 3, all the way to 18, which has 8 valence electrons. We talked about how group 18 was noble gases, they're like royalty, and the reason why they're like royalty is because of their stability. And the reason they're so stable is because they have 8 valence electrons. So in a lot of ways, every other element on the periodic table wants to look like a noble gas. They want to have those valence electrons. We talked about how there were 2 types of ions that could be formed. If you gain an electron, meaning you gain negative particles, you will get a negative charge overall. If you lose electrons, you'll be a positively charged cation overall. This is a reiteration of what I just said, where ultimately elements will gain or lose electrons to look like group 18. Why? Because they're extremely stable. This leads to what's known as the octet rule. The only exception to the octet rule is, of course, helium, as helium actually only has 2 electrons. It doesn't have 8 in total. So the octet rule states that 8 valence electrons and 2 are very, very stable. That, of course, led us into the ideal charge for various groups. This is a table that I do recommend you make an effort to memorize or have at the ready whenever you're studying or practicing your note or practicing questions. The group number does correlate to the ideal charge. Group 1 is +1, group 2 is +2, group 13 is +3, group 14 is +4. After group 14 is when the flip happens. Group 15 is -3, group 16 is -2, group 17 is -1. And of course, group 18 is the noble gases, so they would not want to lose or gain electrons. So their ideal charge is actually 0, aka neutral. That then gave rise to our conversation of periodic trends, where we talked about things like atomic radius, ionization energy, ionic radius, and electron affinity. And of course, we just went over the general trends and directions for these concepts. Today, we are starting something new, continuing in our guise of chemicals and periodic table. We're talking about nomenclature. Nomenclature is the process of naming chemical compounds, or just naming chemicals in general. To understand how to name chemicals, we must first understand the concept of a chemical bond. A chemical bond can be thought of as a force of attraction. Between 2 atoms. B/W is my shorthand for between. A chemical bond can be in multiple different forms. We'll have the most popular single chemical bond, which is comprised of 2 electrons. We have double bonds, which are comprised of 4 electrons. So 2 times double, 2 times 2 is 4. And we also encounter triple bonds, which are, of course, 6 electrons. Although quadruple bonds do exist, they are an active area of research, so they have not entered the general curriculum or lexicon for us to talk about. So we will only really encounter single, double, and triple bonds in Chem 300, but do know that quadruple bonds do exist. They're just very rare. To understand more, we recognize that a chemical bond can be broken up into 2 categories. One of which is known as an ionic bond, and one of which is known as a covalent bond. Naming chemical compounds ultimately comes from identifying what type of bond is present and following its rules. An ionic bond, for instance, is a force of attraction between a metal and a nonmetal. A covalent bond is a force of attraction between a nonmetal and another nonmetal. First question right off the bat, how are we to know what is a metal and what is a non-metal? Well, do remember on your periodic tables, I'll just bring up a copy right here, there is a legend that describes to us the metals, the non-metals, the gases, and the metalloids. That's why it's important for you to regularly carry your periodic table to class. If you happen to forget it, technically the periodic table on the wall to the left of the classroom is color-coded. Those in black text are metals. Those in red text are gases. Those in blue text are liquids. So how do we know if something's an ionic bond or a covalent bond? We simply refer to the periodic table to tell us, is this a metal and a nonmetal, or is it two nonmetals? Let's understand a little bit more about what exactly an ionic bond is. So as I just said, remember, no matter what, an ionic bond is between a metal and a nonmetal. An ionic bond involves a direct transfer of electrons. So electrons are directly transferred from one atom to another. This is our most classic type of bond. You can understand where the term ionic comes from, because if they're being transferred, obviously one is losing, one is gaining. Take, for example, a molecule which we all may be familiar with, NaCl. A lot of us may know this as table salt. NaCl, when written, can be written also in the form with an Na bonded to a Cl. Right there in that center, we have a single line that represents a single bond. And it's on us to understand that between the sodium and the chlorine, there are two electrons that comprise that bond. So these are three ways to write effectively the same thing, telling us the same information. There is a single bond present between the sodium and the chlorine. So if electrons are directly transferred from one to another, one of them has to gain or lose electrons. A very important question, a very important recall question, is why do atoms gain or lose electrons? As we talked about last week, it's so that they can look like royalty. They want to look like those noble gases. They want to look like group 8. So where does this come from? Where does this idea come from? What does it lead to? Well, going back to the example of sodium and chlorine, sodium is in group 1. So it has one valence electron, here just represented with an X. Chlorine is in group 17. So it has 7 valence electrons, here represented with the dots. What we have happening is that the sodium gives up its electron and the chlorine takes it. Electrons are directly transferred from one atom to another. I'll say it once again. Sodium is in group 1, so it has 1 valence electron. Chlorine is in group 17, so it has 7 valence electrons. Sodium will give up the electron. It will transfer the electron to the chlorine, which will absorb it. As a result, even temporarily, you will have a positive sodium ion, a cation, and a negative chlorine ion, an anion, which is, of course, written as our classic sodium-chlorine bond. Right here in the bracket, I like to think of this as just an intermediate, meaning there is a moment, even fleeting, where the sodium will lose its electron. That will form a +1. The chlorine will gain a new electron, leading to its negative charge. So what do the resulting ions look like? Well, sodium had 1 electron to begin with. It gave it up, so it has nothing in the final answer. Chlorine had 7 to begin with. It still has those 6. But remember now that the remaining electrons are found here in the bond. So from the perspective of the sodium has access to 1, 2 electrons. That satisfies the octet rule because it looks like helium. So sodium is happy. Chlorine, you can argue with the same perspective from its direction, has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. Has access to 8. Remember, 6 of them are on the atom itself. The remaining 2 are on the bond. The chlorine resembles a noble gas such as neon with 8 valence electrons. And it's important to remember that within this bond is where the 2 electrons are held. I'm simply drawing them there so you can see that 2 electrons from both atoms are found in this bond. It doesn't matter which is on the top or on the bottom, of course. That's an ionic bond. How do we name ionic bonds then? Naming ionic compounds. Again, I'll write it up here nice and plain. An ionic is a metal and a non-metal. All right, the procedure is actually just 2 steps long. Number 1, the cation, which will almost always be the metal, is written first, aka on the left side of the phrase or name. The anion, which will most commonly be the non-metal, is written second. That is on the right. Step 2, the name of the cation is unchanged. Whereas the suffix of the anion is replaced. And it's replaced specifically with the suffix "ide." So what does that mean? What does that take the form of? Well, let's look at the example we just went over on the previous page, NaCl. All right, hopefully by now we're all very confident that this is a metal and a non-metal. And in this case, we are actually going to go from formula to name. Now, following the rules, the cation, which is traditionally the metal, is written first on the left. Okay, that's that Na right there. The name of the cation is unchanged. Okay, so nothing happens to this sodium. So we know so far that this is simply sodium. The anion, the nonmetal, is written second on the right. That's that chlorine right there. And the suffix of the anion is replaced with "ide." So instead of chlorine, it becomes chloride. And that's it. You simply quickly confidently assume which one's the metal and the non-metal, left and right. And just remember to change the suffix of the anion. That's going from formula to name. What if I had given you the name starting with the name instead? What if I started you with magnesium fluoride? All right, the same approach, but in the opposite direction. On the left is the cation. It's written first, the metal. So we need to be able to read the periodic table, quickly find magnesium for yourself. Magnesium is Mg. All right, we know that it is in group 2. Group 2's ideal charge is 2 plus. Then we have a fluorine. How do we know it's fluorine? Well, remember that if it's on the right, it's the anion, and the suffix is replaced. So fluoride is fluorine. Fluoride is in group 17. It has a -1 charge. So how do we get from the name to the formula using these ions, using these charges? We're actually going to apply something known as the crisscross method. The crisscross method is simple. Upon identifying the charges of the relative ions, we simply cross them. The 2 goes down as well as the 1, but in the opposite directions. They're crisscrossed. We're not taking the charges, we're taking the numbers. So the overall formula becomes Mg1F2. Where does the 1 and 2 come from? Remember, the magnesium has the 2, it gets swung down, it gets crisscrossed. That's how it ends up beside the fluorine. In the case of the fluorine, it has a -1. That 1 gets swung down, becoming right beside the magnesium. We do not swing down the charges, we swing down the numbers. And of course, 1 is conventionally not written. So our final answer is simply MgF2. The beauty of the crisscross method is that it works regardless of what the charge is, because all you're bringing down are the numbers. Take, for example, another molecule, magnesium oxide. Again, magnesium, group 2, it's 2 plus. Oxide comes from oxygen. So oxygen. Oxygen is in group 16. Group 16 has a -2 charge overall. We crisscross, we bring those numbers down. What we see here is Mg2O2. The beauty of the crisscross method is we're actually looking for the lowest whole number ratio. So Mg2O2 can be simplified to MgO. So we're looking for the lowest whole number ratio. There comes every once in a while a situation where you will be using a metal that you're not familiar with. For example, FeO. Fe is iron. It is number 26 on the periodic table. It's in that first row of transition metals. Fe, number 26. Now, if you recall, and actually, I won't even just have you recall, I'm going to show you. According to that little table we talked about, that table that I do expect you to have at the ready, or at least study it. Groups 3 to 12, which is where iron is located, has a variable ideal charge, meaning you cannot just look at the table like you would everything else and predict what the charge is going to be. The truth is, it will depend. So what do we do here? Well, it's actually fairly simple. Although we don't know what iron is, we do know that oxygen is in group 16 and is traditionally 2-. We also know that we can take the rules of crisscross, meaning we don't know what iron is, but we know what the charge of the oxygen is. Since overall it is a 1-to-1 ratio, we can assume that the iron is 2+. Why? Because we know crisscross goes to lowest whole number ratio. If the iron and the oxygen are in a 1-to-1 ratio, the charges must match, 2+ and 2-. This is what tells us that this right here is iron oxide. But wait a minute, Supreet. Why we went through all of that effort to identify the charge of the iron. Looks like we didn't even know it to figure out the name. You just wrote iron oxide. I could have told you that. For transition metals, you are required to include a Roman numeral. And the Roman numeral specifies the charge of the transition metal. TM stands for transition metal. The Roman numerals are required when working with a transition metal. So you do have to put in the effort to figure out the charge because the charge is included in the name. And remember, why does it have to be included? What about something like sodium and magnesium? Well, those are in predictable groups. Groups 1 is +1, group 2 is +2. It's when we're dealing with a variable atom we don't know, so we have to specify. And this works in the other direction as well. What if, for example, I told you, please provide the formula for iron 3 oxide. So this is technically a different charge. Iron 3 tells us that this is iron 3+. The Roman numeral tells us the charge of the metal. The metal will almost always be the cation. And we know that oxygen is in group 16 with a charge of 2-. We crisscross those numbers down. That's what leads us to Fe2O3. The 2 and the 3 have swung down entirely. And let's just do one more, just as a good example. V2O5. We're probably used to it at this point. O is, of course, the oxygen. V is known as vanadium. Vanadium is number 23, so it's part of that transition metal block. What we would do here is quite literally just reverse the crisscross. Right? Remember, what did we do with the charges? We swing them down. So what do we do with the numbers? We swing them up. To no one's surprise, when 2 gets swung up to the oxygen is 2-. That's predictable. That makes sense. The 2 gets swung up. For the vanadium, however, its 5 gets swung up such that this is 5 plus. And you can, of course, recognize the same idea when they swing back down, how you get the V2O5. Overall, the name of this molecule is vanadium 5 oxide. Do we have any questions so far? I see a question in the front, and I'm back. I'll take the one in the front first. Yes. If it's on the left, it's the cation. If it's on the right, it's the anion. The cation is written first on the left. The anion is written right second. I think there was a question in the back here. Yeah. Yes, because in those cases, 2 to 2 can be broken down to 1 to 1. So if it's 3 plus 3 minus, 1 to 1, 4 plus 4 minus, 1 to 1. So we're looking for the lowest whole number ratio. You can see in the example up here for the iron oxide, we had 3 and 2. You couldn't really simplify that anymore, right? You'd have to get into decimals. So you would leave it as Fe2O3. Good question. Anyone else? I see a hand in the front. So I said that transition metals, such as iron, have a variable charge, meaning you cannot just look at the periodic table and know what it's going to be. We do know that since it's a metal, it'll be positive. That's something we can confidently say. But to identify the charge, we need to look specifically at what else we've been given. Here, iron oxide, we know that the oxygen is 2 minus. Sorry, let me use my laser. 2 minus. We also see that the ratio is 1 to 1. That is what tells us this will be 2 plus. Because for them to be 1 to 1, the charges have to match. That is in stark contrast to something over here, iron 3 oxide, where again, the charge is variable, but you could use the reverse crisscross to figure it out. You swing that 3 up, you know it's 3 plus. Again, we know it's a cation because what's on the left written first, it will usually be the positive ion. It's the specific charge value that we're trying to figure out. Good question. Anyone else? All right. What about when dealing with something known as polyatomics? All right, one of the handouts that I passed out at the beginning of class was a single sheet comprised of common polyatomic ions. Raise your hand right now if you do not have a copy of that handout. I'll come around and give it to you. It's a couple of hands. Okay, just hold them up. It'll take me a second. Let me just get this up. All right. Raise your hands. I'll walk around and give you the handout. All right, I'll say this very clearly right now. I do expect you to memorize this table. This is a list behind you. This is a list of common polyatomic ions that you are expected to memorize and know. Here's another. Anyone else missing that handout? Okay, great. Polyatomic ions, as the name suggests, are multiple atoms in a single ion. Name is right there, polyatomic ions. It's multiple atoms in the same ion. Showing you some examples right here. We have NH4 plus, which is ammonium, NO2 minus, which is nitrite, and NO3 minus, which is nitrate. And herein lies the challenge with memorizing these lists of polyatomic ions. That sort of subtle difference, NO2 being nitrite, NO3 being nitrate, is a very common slip up. I do recommend taking the time out using something like flashcards, Quizlet, or Anki to memorize these polyatomic ions. You're going to see a lot of polyatomic ions throughout the course, but these are the only ones I expect you to memorize and commit, especially when it comes to their spelling. I'll show you another one like the nitrite. Let's look at chlorite and chlorate. Chlorite is ClO2. Chlorate is ClO3. So this is absolutely the kind of thing that causes a lot of slip-ups if you're not actively trying to memorize them. With our first exam next Tuesday, you have approximately a week to memorize this because you will not be provided this as part of your exam booklet. You are expected to commit to memory. Okay. So what about polyatomic ions? There is really no difference. They're not treated any differently, really. There are just a couple big assumptions or claims about it. The polyatomic ions are treated as nonmetals, meaning just like anions, they're written second. They're written on the right. But the only thing is their suffix need not be changed. That's why it's so important to memorize the names because they're already set. Meaning you will not be switching nitrite to nitride. There is no need for you to replace the suffix. NO2 is nitrite. No ifs, buts, or else's. So let's just do one or two just as a quick example. First up, Na2SO4. All right, all of you have the handout in front of you, so please identify SO4 on the handout. Don't speak it out loud, but just find it, SO4. All right, what do we have here? On the left, we have the sodium. Okay, that makes sense. Sodium is a metal, so it'll go first. Its name is unchanged. And then the anion is written second, SO4. Looking at your handout, that's just sulfate. That's the full answer for this question. This will actually give me a good reason to segue into something else. Spelling errors. Now, as you can imagine, when we're talking about naming, spelling is really, really important. Of course, there are occasional times when people just make a small typo. And you may be wondering, well, how badly will the typo affect the question, affect the answer? Here's an example. Sulfate. If you made a typo that instead of writing F, you wrote PH, that's still sulfate to me. So you would still get credit for it. That's fine. If you were to misspell this with an I at the beginning, if it were to say sulfate, I'd know what you were saying. I would assume that you just made a mistake under rushed conditions, and I'd still give you the credit. So if the typo is minor and does not change the name, then you'll be fine. However, occasionally, if you change the name, if you make a typo like this with an I, that's actually a different ion entirely. Please look for it on the table in front of you. Sulfate is SO4. And if you just happen to write it with an I instead, just a small, small typo, that would be wrong because that's a completely different ion. So I want to stress again how important it is that you take an active effort to memorize these common polyatomic ions. You will be tested on it in some degree on your exam next week. And they're ions that we will see throughout the semester. You can use Quizlet, Anki, or other type flashcards. But its naming doesn't really change too much from the metals and the nonmetals. Let's try another going from the name. I would like to try magnesium phosphates. We've seen magnesium quite a bit today already, so go ahead and look on the handout for phosphates. PHOS, PHAT. All right. Magnesium is in group 2, so we know that it is 2+. We can see based off of the polyatomic sheet that phosphate is PO4 3-. So what do? We crisscross. We bring those numbers down. That 2 goes down, that 3 goes down. What we end up having is Mg3 PO4 2. Now, let's just take a pause right here. Let's take a look at what I just wrote. Let's zoom in a little bit more. The way I have written this formula, as is, suggests that there are 3 magnesiums, 1 phosphorus, and 42 oxygens. So the way how this is written is inadequate. It's almost incorrect. So whenever we're dealing with that type of situation, we just put a bracket around the PO4, making it clear there are 2 of the phosphates. There are in total 2 phosphorus atoms. There are in total 8 oxygen atoms. The use of the bracket helps us with that. Any questions so far? Okay, so that's ionic. 2 very simple rules. Cation is written first, anion written second, and the suffix of the anion is replaced with "ide." The naming convention is fairly straightforward. Left is the positive, right is the anion, right is the negative. Occasionally, you might have to deal with a transition metal, in which case you would have to include the charge of the transition metal in the name. This takes the form of Roman numerals. You may also be asked some time to convert from formula to name, such as here, iron oxide. And there should be enough information within the name to help you out. Polyatomics are only treated differently in two ways. Number one, they're treated as nonmetals, aka they're written on the right, and its suffix need not be changed. That's ionic bonds. Now let's talk about covalent. And as a reminder, covalent is between 2 nonmetals. All right. So covalent bonding, in comparison to ionic bonding, isn't a direct transfer, but more accurately, it's a sharing of electrons. And we're going to look at 2 examples that really get that point across. The first one is oxygen, O2. All right. So we have 2 oxygen atoms that are coming together. They're each in group 16, so we know they'll each have 6 electrons. Just to separate them, I'm drawing one of the electrons as an X and the other as a dot, just to make it clear that these are from separate atoms. And we know that these atoms, they want an octet. They want 8 in total. We know that. So what's going to happen is they say, hey, if I lend you one of my electrons, can you loan me one of yours? The oxygen atom says, you know what? That's a fine deal to me. Let's get together and do this. So now we have the same oxygens with their electrons, but now one electron from each is being shared right between them, like so. What does this lead to? Well, previously, each oxygen separately had access to 1, 2, 3, 4, 5, 6 electrons. Right now, each oxygen has access to 1, 2, 3, 4, 5, 6, 7 electrons. You can say the same thing for the oxygen on the right. 1, 2, 3, 4, 5, 6, 7. We're not there yet, though. The octet rule says that we need 8. So guess what's going to happen? Another sharing. So now those electrons come together. And what we have in the middle is a total of 4 electrons being shared between the two atoms. From the perspective of the left oxygen, it has access to 1, 2, 3, 4, 5, 6, 7, 8. It's happy. From the perspective of the right oxygen, it has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. It's happy. Everyone's happy. This oxygen can be written as a double bond between the two atoms. Remember, if one bond is 2 electrons, then 4 electrons is a double. Triple bond is 6. And then we still have those electrons on the outside. Those are given some terms. The electrons on the outside are known as lone pairs. We traditionally pair electrons together. It sounds like I'm sounding the fruit pair, but PAIR is what I'm trying to say. So we would say that there are 2 lone pairs on each oxygen atom. And the one in the center, those are known as bonded electrons. So in covalent bonding, there isn't an explicit transfer of electrons. There isn't one giving up and the other taking. They're sharing them together. This isn't the case of O2. What about the other one we want to do together, which is N2? Well, let's apply the same logic. We'll go through it beat by beat. Nitrogen is in group 5. So it has 5 valence electrons. Again, just writing X's and dots to kind of symbolize that they're just from different sources. We know they're going to share. So 1 electron comes from each. All right, there are some electrons in the middle. There are some electrons on the outside. Confirm for ourselves, let's check from the perspective of each nitrogen. It has access to 1, 2, 3, 4, 5, 6 electrons. So not at the octet just yet, but we're on the right track. We're going to share it once again. All right, same idea, same approach. Let's count from the perspective of the left oxygen. It has access to 1, 2, 3, 4, 5, 6, 7. The same thing can be said for the right oxygen. Okay, so we're still not fully satisfied just yet. Guess what's going to happen? Another sharing will take place. So between the two nitrogens, we have 6 electrons in total. Now let's check from the perspective of the left oxygen. Let's switch things up actually. From the perspective of the right oxygen, it has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. Each nitrogen is happy. Since there are 6 electrons between them, we know this is a triple bond. And it's covalent bonding that gives rise to these multiple bonds, double bonds, triple bonds, and the like. They're sharing electrons. They keep sharing. The other important takeaway is that covalent bonding, just like in the case of oxygen and nitrogen, proves and verifies the existence of what are known as diatomic elements. Diatomic elements are two of the same atom, shown here generically with X2, as that's how the atom exists in nature. You're all very used to oxygen, O2. You're probably also used to nitrogen, N2. So those are probably two you already recognize as being diatomic. But there are others. H2, F2, I2, Cl2, Br2. These are a list of the diatomic elements that you will encounter on the periodic table. I want to be clear on something. This is how they exist in nature. The covalent bonding that takes place is so easy that you will never find oxygen just floating around. It will always be O2. You will never find just a nitrogen floating around. It will always be N2. Any questions so far? This is the details of covalent bonding. Now we're going to talk about how to name them. Okay? Naming covalent compounds is what's up next. So obviously the big difference between ionic and covalent is the idea that the electrons are being shared. Since they're being shared, there isn't an explicit cation, there isn't an explicit anion, simply because, well, no one's losing anything, no one's gaining anything, they're just simply sharing. So if you recall, when we talked about the ionic, we talked about in terms of the cation being written first, the anion being written second, the positive and negative. When that doesn't quite work, doesn't quite play with covalence, how exactly do we name it? Well, it might surprise you to know it's pretty much the exact same set of rules. The elements in the lower group number assumes the role of the cation. AKA, it is written first and an unchanged name. So even though a cation does not explicitly exist as in ionic, we just simply assume that the lower group number takes the role of the cation when it comes to naming. Number two, the element in the higher group number assumes the role of the anion. where, of course, it is written second, and the suffix "ide" is used. So far, naming the two species, it follows a very similar pattern. What's on the left is presumed to be positive, written first, unchanged name. What's written second is presumed to be the anion, written second, and of course used "ide." The key difference is in number 3. Greek prefixes are used to quantify the atoms. What are some examples of Greek prefixes? There is mono, di, tri, tetra, penta, hexa, hepta, octo, nona, and deca. This, of course, refers to the numbers 1, 2, 3, 4, all the way to 10. Mono is the only one that is not conventionally used, simply because, just like in algebra, we don't really write 1x, we simply write x, and of course it's implied to be 1. So mono is most commonly not really used. So let's try an example, taking all of our rules together and trying to name a covalent compound. If given the formula N2O5, all right, let's get our periodic tables at the ready. We're going to look for nitrogen and oxygen. All right, take a second to look for ourselves. Where is nitrogen? Nitrogen is in group 5. I'm sorry, 15. Oxygen is in group 16. The atom in the lower group number assumes the role of the cation and is written first. The higher group number is written second and assumes the role of the anion. Is this the only way you could have figured that out? No. Why? Nitrogen's on the left, got to be the positive. Oxygen's on the right, got to be the negative. So then the name simply becomes nitrogen. Remember, it assumes the role of the cation. Nothing happens to the name. Oxide. Oxygen assumes the role of the anion, and its suffix is replaced. The big difference is we need Greek prefixes to indicate quantity. There are 2 nitrogens, so we write di-nitrogen. There are 5 oxygens, so we write pentaoxide. Now, does this make sense? Does this actually line up with what we know? Yes, it does. Now, earlier, I just told you that the one on the left assumes the role of the positive charge. Now, nitrogen is in group 5, which I've told you its ideal charge is -3. It's in group 15. So how is it positive? Well, let's take a second to look at it. If we were to reverse crisscross these numbers, we would get N5 plus and O2 minus. Remember, again, we know that the left one is the cation, so we know that when we swing the 5 up, it'll be 5 plus. When we swing the 2 up, it'll be the negative. Now, O2 minus, that makes sense. It's in group 16. But N5 plus, this doesn't feel right. But it's okay. Does anyone want to take a guess why nitrogen, having lost 5 electrons, is perfectly okay? I see a hand. That is correct. That's not the answer I was looking for. Think about electron count. Nitrogen normally has 7 electrons. How many electrons will it have after losing 5? 2. Is there anything special about 2 electrons? Helium. The octet rule. So it's not the direction. Let me go back to the periodic table just to show you. It's not the direction we're used to. We're used to gaining 3 electrons to look like neon. But you go back, lose 5 electrons, you end up looking like helium. So it's perfectly reasonable. They still both look like noble gases. So there's nothing wrong with nitrogen taking on that positive form. What about something like if I give you the name sulfur hexafluoride? And I ask you, from the name, give me the formula. Now, the beauty of covalent compounds is that to go from name to formula, there actually isn't that much thinking behind it because everything you need to know is in the name. There's no guesswork. Sulfur, there's only one of them, so it's S. Fluorine, and before the fluorine is hexa, telling us there are 6 of them in total. How did we know that there was only one sulfur? Well, remember, if it's not included, you are expected to assume that there is a mono. It's just like in algebra. We don't really write 1x, we write x. So mono is typically dropped. There's nothing wrong with writing it. You just added the few seconds it took to write it to your overall exam time. But everything you need to know about the name, everything you need to know about the formula is in the name. Do we have any questions? Okay. Now we're going to turn our attention to today's problem sets. Raise your hands if you don't have a copy of the problem set. Yeah, it's like the same people with the hand up. Behind you. Behind you. All right, this is our third problem set. So we have a good idea of what we're going to do by now. I'm going to go through a couple questions with you. You're going to do a couple questions on your own, and some of them will be extra credit. So let's get the extra credit straight out of the way. Number 1, the extra credit is entirely page 5. The extra credit is the entirety of page 5 and the entirety of page 3. Pages 3 and pages 5, the entirety of them are your extra credit. Our exam is on Tuesday next week. All of the extra credit will be due Monday nights. So hopefully you've been keeping up with the extra credit so you don't necessarily need to do all of them at once this weekend. But of course, remember the idea behind the extra credit is you'll be studying and practicing for the exam anyway. You might as well get some credit for it. Okay. I'm going to do a couple questions. We're going to start with problem 1 on the first page. The instructions say, please provide the molecular formula of the compounds that result below. The way how these tables are to be read is a multiplication times. You're going to get the combination of these two right here, the combination of these two, so forth. If I ask you specifically for down here, it's combining the sulfate with the osmium. So you will need that common polyatomic ions. Get that ready. We're going to do the entirety of the first row. I want you to notice a couple things. Notice that over here in the highlight, I did give you the charge. CO is cobalt. Cobalt is number 27. It is a transition metal. Remember, I've told you, you cannot look at the periodic table and know what the charge should be. So it's on me to include somewhere in the question what the charge is. In this case, I'm telling you for cobalt, it's 3+. And then the columns are all of the anions. You'll see they have the classic anions, oxygen and chlorine, as well as some polyatomics over here. So we're going to put them together. We're going to use the rules that we've gotten so far. First up, we know that the cation is written first, cobalt 3+. We know that the anion is written second, NO2-. To get the formula, we will apply the rules of crisscross. That 3 gets swung down, and so does that -1. What we end up having is cobalt 1. Remember that 1 gets swung down. We don't usually write 1, so we leave it as CO. And then we have the nitrite, NO2 in brackets, because their 3 gets swung down. I do encourage you in your practice to also try to name the compounds that result. It's not an explicit question on the worksheet, but it's good practice regardless. Because after getting the formula right here, we can name this. The transition metal, the cation is unchanged. It's cobalt. The transition metal, we do need the charge in Roman numerals. The charge has been told to us as 3+. So cobalt 3. And the name of the anion is nitrate, right? No. What is it? Nitrite, right? So there's an I right here. So be careful about that. Let's do the same thing to the next cell with SO4 2-. All right, let's put the cobalt right beside it just so I can have an easier time. Putting them together, the 3 gets swung down, the 2 gets swung down. The resulting formula is cobalt 2 sulfate with a 3. Remember, we put these things in brackets to make it clear, because without the brackets, if you don't write it properly, it's like you're saying there are 43 oxygen atoms, which is, of course, incorrect. The name of this compound is cobalt 2 sulfate. Am I right? What's wrong with it? The 3 charge. Very good. One common mistake that people make is they think that the Roman numerals is based off of the number right after the cobalt. It is not. It's based after the charge. So instead of cobalt 2, this should be cobalt 3. All right, we're still working with cobalt. And actually, let's just keep going. I need to move over here. Yep. Cobalt 3+, cobalt 3+, cobalt 3+. All right, looking at the next one, we have here cobalt 3+ with PO4 3-. This is a situation where the charges equal one another, 3+, 3-. We can crisscross. If we crisscross, we would get, generically A, generically B3. But we're always looking for the whole number ratio, the lowest whole number ratio. So we can simply say that the product here is CO PO4. Why? I'll say it again just so I'll write it out so we're explicit. When you crisscross, you get CO3 PO4 3. When determining formulae, we look for the lowest whole number ratio. 3 to 3 can be further simplified So 1 to 1. Moving on with the same idea. Hopefully we're kind of getting in tune with the trend going on here. We're just crisscrossing numbers. I should be able to write this and you have no issue. CO2, O3. The 2 from the oxygen gets swung down. The 3 from the cobalt gets swung down. And then finally, for the last one, the chlorine, we have COCl3. That's the entirety of the first row on the first page. I would like to do row 2 from page 4, specifically the one with the bromine. All right, first things first, notice on this page, there are a couple cells that are blacked out. That means you cannot get the formula for those because they're in the same group. There's no way for you to know which one's a cation, which one's the anion. So the blacked out cells, you're not responsible for, you don't need to do. All right. We have here phosphorus and bromine. Looking at where they are on the periodic table, we do have a situation where they're both non-metals. We don't know which one will be which. So we look at the periodic table. Phosphorus is in group 5. Bromine is in, group 15. Phosphorus is in group 17. The rule states that the lower group number is written first, P, and then the higher group number is written second. We know that the higher group number takes the role of the anion. That's normal. Bromine is in group 17, so it has a -1 charge. We know, of course, this means that the phosphorus must be positive. But what number exactly is it? See a hand right there, but I just want to give people a chance to think. I'm ultimately asking. The phosphorus is going to be plus, but a number is going to be in front of it. Is it 1 plus, 2 plus, 3 plus, or what? 2 plus? I saw your hand. What do you think it is? 3 plus. Any other options? Okay, why do you think it's 2 plus? Are you guys saying the 2 down here? This is not one of the diatomic elements. All right, you said 3. Why did you think 3? Okay. So unfortunately, neither one is correct. Remember, when we think about why do you think it's +5?
Because it would give it 2.
It would give it how much? You sure about that? 15 minus 5 is not 2. Okay, so he was on the right track. It is 5 plus. Remember, all of this comes back to royalty. It always comes back to noble gases. Phosphorus is number 15. It's not going to go towards argon. Why? Because it's not the anion. It's going to lose. So what's the other closest noble gas to phosphorus? Neon. 15 versus 10. So it loses 5 electrons. That's what tells us this is going to be 5 plus. This part is where the trickiness of covalent compounds come in, because it's something you have to actively pay attention to. You're getting a load of practice from this one worksheet because this is a very challenging topic. If you don't fundamentally understand naming and formula, it's the kind of thing that you're going to suffer for future topics. Because come 2 weeks from now, I'm not going to be breaking down these charges. I'm going to be saying to you, phosphorus bromide combines with sodium chloride to form magnesium sulfate and water. Write it down, right? You got to know what these names are. I'm not expecting mastery today. I understand that, but your first exam is next Tuesday, so you have less than a week. Let's try another one on this. Let's do This one right here, the phosphorus and the oxygen. I've just put a little star beside it so you know which one I'm referring to. All right. Phosphorus is in group 15. Oxygen is in group 16. The lower group number is written first. It assumes the role of the cation. The higher group number is written second. It assumes the role of the anion. Oxygen being an anion makes sense. It's in group 16. We regularly expect it to be 2-. That's fine. But for the same reason encountered before, phosphorus is 15. It will lose 5 electrons to look like neon. As a result, when we crisscross, we bring that 2 down, that 5. The overall answer is P2O5. Yes.
Phosphorus.
So it becomes ultimately, we have a choice. Let's use this one right here, the phosphorus and the oxygen. One of them will be positive, one of them will be negative. We know from our rules, the lower group number is expected to be positive versus the higher group number is expected to be negative. Now, oxygen is right by neon. So it being anion makes sense. It just gains 2 electrons. That's what we're used to. The phosphorus has to become a cation. It has to lose electrons. You're not going to lose electrons and get to 18. You have to lose 5 electrons specifically to look like neon. Yes?
What if they're in the same group?
I would not give you such a question. That's why these are blacked out on the table. Good question. Yes?
What the answer on these sheets?
I'll put it to you this way. This right here, P2O5 is the final answer. Yeah, P2O5 is the final answer. Any other questions? Yes? Yeah, sure. Let's do that one. On the first, top one right here. Yeah, that's good. All right. So student wants to do the first row with NH4 plus. All right. I've already defined for you that this guy is cationic plus. So there is no choice for everything else. For this one, it's just a matter of, okay, we have NH4 plus. Phosphorus is expected to be negative. Phosphorus is in group 15. So it'll be negative 3. Crisscross comes down. This becomes NH4 in brackets 3 phosphorus. See, there is no choice to be made here because the NH4 is already given to you as a positive ion. You don't need to decide if it's going to be positive or not. And if that's positive, everything else must be negative, which is what we expect. Let's try the next one. Se. Se is selenium, number 34. Selenium is in group 16. So selenium is expected to have an ideal charge of -2. And we have NH4s +1. Crisscross tells us this will be NH4 2Se. Okay. I'd like to do just a couple from problem 2. I'm going to specifically do these 3 that I've highlighted. All right. First up, we have ZnSO4. You should be able to very quickly recognize SO4 as a polyatomic. Take a second to try to find Zn on the periodic table. Zn is a transition metal. It's number 30. All right. There being a transition metal tells us we need to figure out what the charge is going to be or is and reflect that in the name. We see here that in the formula, this is a 1-to-1 ratio. There is 1 zinc, 1 sulfate. If sulfate is -2, what must the zinc be? +2. Once we figure that out confidently, we can say that this is zinc. Sulfate. Is my answer as written correct? What am I missing? Roman numerals. And how much do I need in the bracket? 2. Zinc 2 sulfate. All right, the next one on the right, LiCl. Take a look for Li and Cl on the periodic table. Li is lithium, number 3. And chlorine, that's in group 17. This is not a transition metal. This is not a covalent molecule. This is actually the simplest case. This is just writing them with the rules we have. Lithium chloride. No Roman numerals needed, no Greek prefixes needed, just the name. Because the Roman numerals is what tells us the charge of the transition metal. There is no transition metal here, so no charge is needed. Now, you might be asking, well, couldn't we still write a 1? You could. It wouldn't be wrong. You just cost yourself the few seconds it took to write the 1. It's just not needed. For transition metals, it is needed. And then lastly, the N2O4, nitrogen and oxygen are both non-metals. The one on the left assume the role of the cation. So we have nitrogen, aka its name is unchanged. The one on the right, written second, assumes the role of the anion. So its suffix is replaced. This is oxide. The only thing that's left for covalent compounds is the Greek prefixes that quantify the amount. We see from the formula there are 2 nitrogens. This is what tells us this will be dinitrogen. We see from the formula there are 4 oxygens. This is what will tell us this will be tetraoxide. So the full name is dinitrogen tetraoxide. In our last minute, do we have any questions? All right, we'll end lecture for today. Remember, the extra credit is entirely of page 5 and entirety of page 3. If you have any questions, come talk to me now. If not, I'll see you guys on Thursday.